companding. Sometimes what happens is, uh, assume my input signal value is more than 2V, let us suppose. If it is more than 2V, okay? Just little more than 2V, let us suppose. Just little more than 2V. But we have fixed the number of quantization levels. We have fixed the number of quantization levels. And my signal is, instead of minus V to V, my signal is something like this. A little more than V. I designed my everything, my quantizer, PCM, encoder, everything. But fortunately or unfortunately, the input signal size is a little more. Now, as a result, there will be some loss of information, and it should not happen. So we need to figure out some way, even to accommodate this a little more signal also. So in the process of accommodating this extra signal, I can say extra signal, we discuss about the concept of companding, where companding is nothing but, here two terms are involved in companding. One is the first term called compression. I need to compress the input signal so as to fit in between minus V to plus V, because my quantization levels are already fixed. So this compression of the signal should be done at the transmitting end. Then the second part is expansion. I'll take a very small example. Maybe many of you have done this experiment. Assume I have a glass of water. Okay. And you have a flexible straw like this. You have a flexible straw. And what we do is, we try to push this straw so as to fit into this glass. Then the straw will take like this. Most of you have done this experiment, knowingly or unknowingly. Are you following me? Have you done this earlier? Keeping the flexible straw, pushing the flexible straw to fit into the glass top. Yes or no, at least.
Yes, sir.
So this is the straw with no expansion, no compression. And this is with compression. So the same thing that we want to do here. The same thing that we want to do here. So I have a let it be my input signal Vi, and this is my output signal. I want to work out a circuit. So without expansion, this is the signal. Without compression, this is the signal. So after compression, now on the other hand, to the negative values also, I need to do the same thing by negative values. So as to fit into the range minus V2 plus V. So this is now my new V naught. We compressed the signal like this. So this is the compressed version. And this is without compression. Okay. So this is the Vi max plus V and minus V. Okay. Minus Vi maximum value. So we fit into that. The extra portion also we somehow we kept within the limit. Okay. So this is what we call it as the process of compounding. Now what we do at the receiver, we do at the receiver the reverse process. The reverse process such that this signal after decoder, after low pass filter, we expand the signal. Whatever the amount of compression you made here, the similar amount of expansion will be made at the receiver so as to get your original signal back like this. Okay. Clear?
Yes, sir.
Okay. So for the time being, I'll stop here. There are two types of companders. One is ALA compander. Another one is mu-law compounder. After all, there is a difference between the relation between y equal to f of x. See, this is y equal to f of x, right? This is my y and this is my x. So this curve will give the y equal to f of x relation. The same thing for a law and mu law. There are some constants called a and mu. I'll tell those equations tomorrow. A law and mu law compounders.